Good evening. Today our topic for discussion is Chapter 12, Atoms. Ernst Rutherford, a research student of J.J. Thomson, proposed a classic experiment of scattering alpha particles by atoms to study the atomic structure. The experiment was performed by Geiger and Marsden. Marsden was just a 20-year-old student who hadn't even got his bachelor's degree, and they performed this experiment 5 years after Rutherford proposed this theory. And in that experiment, what they did is they had a beam of alpha particles directed onto a thin gold foil, and the scattered alpha particles were observed using a detector. A typical graph of the number of scattered particles with the angle of scattering. The angle of scattering is the angle. This is the initial direction of the alpha particles, and angle of scattering is the angle through which these alpha particles have been deflected. So this typical graph is, this graph shows the number of scattered particles with the angle of scattering. And from the graph you will see that maximum number of alpha particles went undeflected. Here, that we have most of them passing through the gold foil without any deflection, and that's why we have maximum number of scattered particles for angle of scattering theta close to 0. And very few particles were deflected backwards, very few particles had a scattering angle greater than 90 degree. That is, very few of them were deflected backwards. And this, Rutherford argued, is because most of the atom is empty space, and because of which this alpha particle, being positively charged, does not suffer any collision and can pass on without any scattering. The very few particles that were directed towards the nucleus, he said, was where the all of the positive charges of the atom was concentrated, and if an alpha particle suffered backward deflection, it is because it is experiencing a large repulsive force from that positively charged nucleus. So his model, the Rutherford model of the atom, had all of the positive charges of the atom concentrated at the center called the nucleus, which occupied a very small space in the atom, and the rest of the atom most of it was empty space, with the electrons revolving around the nucleus like the planets revolve around the sun. Now, as we discuss Rutherford model, we need to look at two definitions. One called the impact parameter. So, here if we have the gold nucleus, let's say this is the gold nucleus, Ze, charge, Z being the atomic number, and inside the nucleus, the atomic number tells us the number of protons, and the protons have the same charge as an electron but positive. And now if I draw a line through the center of the gold nucleus, let us represent this as the initial velocity direction of the alpha particle. So as this alpha particle approaches the gold nucleus, because of repulsion, it will be scattered, and this angle is what we call as the angle of scattering theta. Now, the perpendicular distance between the line drawn through the gold nucleus and the initial velocity direction of the alpha particle is what we call as the impact parameter. This impact parameter determines the trajectory of the alpha particle. That is, suppose the impact parameter B is 0. That means the alpha particle is approaching here like this. Then you know that because it is going to be repelled by that large repulsive force, it's going to deflect back with an angle of 180 degree, and therefore if B is 0, then the scattering angle is 180 degree. Whereas if B is infinity, that is the alpha particle is far away from the gold nucleus, it doesn't suffer any deflection, and therefore the scattering angle will become 0. So if B is infinity, very far away from the gold nucleus, then theta, the scattering angle theta, will be 0. So this impact parameter determines the trajectory of the alpha particle. The other thing that I want to discuss with you is the distance of closest approach. So now if we have this alpha particle, whose the gold nucleus, whose charge on the nucleus is plus Ze, Z being the atomic number, and if your alpha particle is approaching here along this line, we know that at some point the alpha particle will return back because of the repulsive force between the electrostatic force of repulsion. So this distance up to which the alpha particle can approach, the closest distance up to which the alpha particle can approach the gold nucleus before being deflected back is what you call as the distance of closest approach, and I'm going to call it as R0. Now here I'm going to give you an expression for this distance of closest approach. So as this alpha particle approaches and deflects back, its velocity reduces to 0, which means its kinetic energy reduces to 0. So the whole of the kinetic energy is converted to the potential energy between the two charges. So we have K is equal to, potential energy we know is 1 by 4 pi epsilon 0 Q1 Q2. So we have ZE here into the gold nucleus is, as you know, He24. So we have 2E, the proton has 2 protons. So the charge on the nucleus will be 2E, both positive, divided by distance between the two charges, that is R0. So we may write R0 is equal to 1 by 4 pi epsilon 0 2 ZE square by K, where K is the kinetic energy of the approaching alpha particle. So this expression will give you the expression for the distance of closest approach. Now the Rutherford model had drawbacks. The first drawback being that according to this Rutherford model, we know that the electrons revolve around the nucleus. Now as these electrons go around in a circular orbit, we know that they are accelerated charged particles because there is a centripetal acceleration. And in the chapter EM waves, I taught you that accelerated charged particles give out EM radiation, electromagnetic waves, produce electromagnetic waves. So because of these electrons being accelerated charged particles and because they give out electromagnetic radiation, they must lose their energy and finally spiral down and fall into the nucleus, which does not happen. So that is one drawback of the Rutherford model. The second one is, see, we know that this is radiating energy and therefore it will now spiral with smaller radii, smaller circular orbits, and because of which there is a continuous change in its frequency, in its energy and therefore its frequency, and which means the spectrum of that EM radiation must be a continuous spectrum. To the contradiction to this, what we observe is not a continuous spectrum but a line spectrum, about which we will be discussing towards the end of the session. So this was a contradiction. We expect a continuous spectrum, but what we see is a line spectrum. So these are the drawbacks of the Rutherford model. Now Niels Bohr put forward some modifications to this Rutherford model, and his modifications were put forward in the form of 3 postulates. Bohr's postulates, 3 of them. The first postulate states that the electron can revolve around the nucleus only in certain orbits, which he called the stable orbit or the stationary orbit. And when the electron goes around the nucleus in a stable or a stationary orbit, it does not radiate energy. That's the first postulate. In the second postulate, he gave a definition to these stable or stationary orbits. He said stable orbits or stationary orbits are those orbits in which the angular momentum of the electron, which is L, which is last year we learned is angular momentum is R cross P. P is M into V. So L is mvr, should be an integral multiple of h by 2 pi, where n is any integer and h is the Planck's constant. So this is how he gave the definition for the stable orbit or the stationary orbit. The third postulate says that an electron can make a transition from a higher energy level to a lower energy level by giving out a photon whose energy is equal to the difference in energy between the initial state and the final state. That is, the third postulate says the energy of the photon given out when the electron makes a transition from an initial state of energy EI to a state of energy, the final state of energy EF, will be the difference in energy between the two levels. Now at this point we need to derive an expression for the radius of the nth orbit of the hydrogen atom and also for the energy of an electron in the nth orbit of a hydrogen atom. And that is what we are going to do now. First we will derive an expression for the radius of the nth orbit of a hydrogen atom. Okay. Now we know that in a hydrogen atom we have a single proton, and in the orbit we have the electron, and this is the radius of the nth orbit of the, it could be the first, second, third, whatever. So we are going to find the radius of the nth orbit of a hydrogen atom. Now as this electron moves around in a circular orbit, we know it is experiencing a centripetal force, which we know is given by the formula mv square by r. Should be given by the electrostatic force of attraction between these two, which in the first chapter we know the electrostatic force of attraction is K, which is 1 by 4 pi epsilon 0 Q1 Q2 by R square. So we may write this as K into both E into E, that is E square by R square, which I will write as my first equation. I don't use the negative sign here because we have learned in the first chapter that we are only writing the magnitude. We have attractive force because one is positive and the other is negative. We have an attractive force and we have written the magnitude here. Now from this equation I may write an expression for R as Ke square by mv square, which I'll take as my second equation. So I'll just write it down here because we need this later. mv square equal to Ke square by R. I have written down the first equation. Okay, we'll need this later. So here, this is the first expression for R that I've got, but I cannot accept this equation because V is not a constant. As the orbit, for different orbits, the velocity of the electron in different orbit is different. So what we need is R in terms of the principal quantum number n. Everything else should be a constant. So we go on to write the second postulate, Bohr's second postulate, which says mvr should be equal to an integral multiple of h by 2 pi, from where I may write R is equal to nh by 2 pi mv. Okay. Now here, this I will take as my third equation because again I cannot accept this R simply because of the presence of V. Now what I will do is I will equate these two equations, get an expression for V and then substitute it here so that we may get R in terms of n only. So here we have, wait, let me write this equation somewhere here, mv square equal to Ke square by R. Okay. Okay, here, now I am going to equate the two equations for R. So we have Ke square by mv square equal to nh by 2 pi mv. Now I cancel this n and I may write this v also, and I may write my expression for v as 2 pi Ke square. 2 pi I have taken it here. 2 pi Ke square is by n into h. By n into h will be the velocity of the particle in the nth orbit. That I will take as equation 4. And I am going to substitute that fourth equation in the third one to get an expression for R. So that is R is equal to nh by 2 pi m here, and V I am going to substitute this. So this is n into h by 2 pi Ke square. So I get n square h square by 4 pi square m Ke square. Now you will notice here that this is Planck's constant. 4 pi is another constant. M is the mass of an electron. K is 1 by 4 pi epsilon 0, again a constant. E is the charge on an electron, 1.6 into 10 raised to minus 90. So this whole thing is a constant, which I may replace as A0, the constant, whose value is 5.3 into 10 raised to minus 11 meter. So that I may write R as A0 n square. Showing you that the radius is proportional to square of the quantum number n. Now here, we call this A0 as the Bohr radius, defined as the radius of the first orbit of the hydrogen atom. That is, if you put n equal to 1, suppose you put n equal to 1, you see R is going to be equal to A0. So this A0 is called the Bohr radius, which is defined as the radius of the first orbit of the hydrogen atom. Okay. Now, so we have got an expression for the radius of the nth orbit, and now we are going into finding out the energy of the electron in the nth orbit. As you know, an electron will have the total energy, let's call it as En, energy total in the nth orbit, is the sum of its kinetic energy plus the potential energy. The kinetic energy is, we know, half mv square. So, which is from our equation here, half mv square would be what? Ke square by 2r, right? Because we know mv square is equal to Ke square by r. I divided both sides with 2. So, I may write kinetic energy of the electron as Ke square by 2r. Potential energy from the second chapter, you know, is K Q1 Q2 by r. So, I'm going to substitute that as K Q1 Q2, the proton and the electron both having the same charge. So, Ke square by simply r, but with a negative sign, because you know, between the electron and the proton there is an attractive force, and when the force is attractive, the potential energy is always negative because they are unlike charges. So, we have minus Ke square by r, giving us this expression as the total energy will now be half minus 1, so minus Ke square by 2r. At this point, it is important to note that the kinetic energy is actually, this magnitude wise, the kinetic energy is equal to the total energy. Can you see this? Kinetic energy is Ke square by 2r, so is total energy, except that the total energy is negative, but the kinetic energy is positive. When you compare the total energy to the potential energy, you will see that 2 times the total energy will be the potential energy. Into 2 and you get the potential energy. So please remember, kinetic energy and total energy are equal in magnitude. Potential energy is twice the total energy. Okay. Now I am going to substitute for R here as this is K is 1 by 4 pi epsilon 0 into E square by 2 into, I am going to substitute for R here from here. So this will be 4 pi square m K E square divided by n square h square, or I can also make one more substitution as instead of K here, I can substitute this as 1 by 4 pi epsilon 0. So if I make this pi square, I cancel here. Then this 4 and 4, I have this En now equal to minus m e raised to 4 divided by 8 epsilon 0 square n square h square. Now this is mass of an electron, charge of an electron. This is epsilon 0, the permittivity. N is a principal quantum number, h is Planck's constant. So I can substitute for all these and get the equation. En is equal to minus 13.6 divided by n square, and this value for energy will be in electron volt. So this is what we need to remember. The energy of an electron in the nth orbit is inversely proportional to n square. So based on this, we may draw the energy levels. That is, if you are going to represent the electron energies here in electron volt, we have the ground state n equal to 1, which corresponds to minus 13.6 electron volt, because we have a formula minus 13.6 by n square. So if I put n as 1, this is the ground state, and that corresponds to a level of minus 13.6. The next one, that is n equal to 2. We have minus 13.6 by 4 will be minus 3.4 electron volt. The next higher will be n equal to 3, which is minus 13.6 by 9, which is minus 1.5 electron volt. The next one will be n equal to 4, which is minus 13.6 by 16 is minus 0.85 electron volt, and so on. We then have the n equal to 5 and so on till infinity, where n equal to infinity will correspond to an energy level 0. So you will see that the least energy, which is the largest negative value, corresponds to the electron in the ground state, which is closest to the nucleus. So which means if you want to remove an electron from the ground state, you have to supply an energy which is equal to plus 13.6 electron volt, and that is what you call as the ionization energy. Now, a hydrogen atom in the room temperature will be in the ground state. So, if by some process like electron collision, the hydrogen atom can raise its electron from a lower energy level to a higher energy level, and then the hydrogen atom is said to be in the excited state. So from that excited state, the electron can make a transition from a higher energy level to a lower energy level by giving out a photon whose energy h nu will be, like I told you, h nu is equal to EI minus EF. Now EI, we got the formula as minus n square h square by, minus me raised to 4 by 8 epsilon 0 n square h square, bracket I will write this as 1 by ni square plus 1 by nf square. Minus here, because I have taken the minus here. Okay. Now here this is h nu. So I may write this as hc by lambda, which is equal to me raised to 4 by 8 epsilon 0 h square bracket. I take the negative sign inside, so that I may write this as nf square minus 1 by ni square. I took the negative sign inside here. Now if I remove this from here, 1 by, this will have a c here and a cube, h cube c, and this is what you call as the Rydberg constant, and we have a final formula, Rydberg constant bracket 1 by nf square minus 1 by ni square. Now this lambda is the wavelength of the photon emitted when an electron makes a transition from a higher energy level to a lower energy level. The first spectral series was observed by a school teacher called Johann Balmer, and the series that he observed was in the visible region, and it was named after him, the Balmer series. There were other series also, like the Lyman, the Passion, the Bracket and the Fun series, all named after their discoverers. The Lyman series is when an electron makes a transition from to the final level should be n equal to 1. So if the transition can be from n equal to 2, n equal to 3, n equal to 4, n equal to 5, and let's say from n equal to infinity and so on. So this series is what we call as the Lyman series. The next one is what I said in the visible region, which we have transition to n equal to 2. So from n equal to 3 to 2, or n equal to 4 to 2, or 5 to 2, and so on from infinity to 2, that series was called the Balmer series in the visible region. The first line that you see here, this will have the longest wavelength because of the transition. The shortest energy gap will correspond, because we know delta E is equal to hc by lambda. So the longest wavelength will be for that emission of the photon between n equal to 3 and n equal to 2. That line corresponds to the longest wavelength, that is the red line, and it's called the H alpha line. The next line, which is from n equal to 4 to n equal to 2, the next wavelength will correspond to the blue-green wavelength, and that's called the H beta line. This is the H beta line. And the very next one, that is from n equal to 5 to 2, that is called as the violet region. That's called the H gamma line, and so on. We next have the transition to n equal to 3 called the Passion series. So it can make a transition from higher levels, 4, 5 and infinity, and that's called the Passion series. The final state should be n equal to 3. When the final state is n equal to 4, it's called the Bracket series, and when the final is to n equal to 5, it's called the Fund series. So these are all named after their discoverers. And this spectrum is what you call as the emission spectrum, because it is when an electron makes a transition from a higher level to a lower energy state, giving out a photon of that corresponding wavelength. You can also have the absorption spectrum, which will be a dark line, because the electron can absorb a photon and make a transition from a lower level to a higher level. So because it is absorbing that photon, the spectrum will be a series of dark lines, and it's called the absorption spectrum. The explanation given by Niels Bohr to the atomic structure was a very brilliant explanation, and he was awarded the Nobel Prize in 1922. So this is all you need to know in this chapter, atoms, from an examination point of view, and we will discuss the problems later. Thank you.